Hi students, welcome to the next video, which is going to be on covalent network lattices. So we've finished with covalent molecular substances. So these are the guys that don't form molecules but are made of the non-metal elements. And because they don't form molecules, they actually form what's referred to as giant structures, not like mountains of things, but on the atomic scale they're made up of massive amounts of atoms joined together covalently. They don't occur as molecules. Can't stress that enough. So because they're bonded covalently together, they form this three-dimensional lattice, and we'll have a look at what that lattice looks like shortly. But the most common examples of these covalent network lattices are diamond, silica dioxide, sometimes known as quartz, silicon carbide and tungsten carbide. Now, why are these two guys highlighted? Because they're the main two that you're going to encounter. Either they're named in questions or you're given the properties of these two, but they're not named, but you need to recognize them. So we're going to look a little bit closer at diamond, and we'll also look a little bit at silica dioxide a bit more. But what we learn about those two are the properties of covalent network lattices altogether. So diamond, it's known as an allotrope of carbon. So it's made up of carbon, just carbon atoms joined together. And an allotrope means that carbon can be in a variety of forms, and this is one form of carbon, which is diamond. And we'll in the next video we'll look at another form of carbon, which is known as graphite. It's still made up of carbon, but it's the way the carbon atoms bond together that determine whether it's graphite or, in this case, diamond. Now this is a cut diamond. You see them in rings. There's a cut diamond as well. There's a naturally occurring diamond. They don't come out of rocks looking like that. They come out looking like this, and sometimes you can see that they come out looking like this, where you have little pyramids, two pyramids joined together, and that's their natural crystalline structure. And some people don't realize that diamonds can come in a variety of colors as well, and that some of the colored diamonds are just as expensive or more expensive than the clear ones. Now on our OneNote there'll be a video on how diamonds are formed, which you can watch just to make sure that you know. So this is the structure of diamonds. We said that the diamond is an allotrope of carbon, so each of these spheres is a carbon atom, and each of these rods represents a covalent bond. And so we know that carbon wants to form 4 covalent bonds. We did that when we were doing our Lewis diagrams. And so this carbon here has 4 bonds here, okay, to other carbons. So each of those bonds is a covalent bond, which is very strong. And here they've tried to show that all the carbons form this tetrahedral shape. And so if we looked at any carbon, they would be bounded by a tetrahedral shape. And you can see here that because of the arrangement, there's no real planes of weaknesses in diamonds. And that's what makes them the hardest known, well, used to be the hardest known substance known on Earth. Now, because they're very hard, because they've got those covalent bonds, there's a lot of uses that rely on that hardness. And one of the uses of diamonds is in diamond drill bits, not drilling little drill bits that you put in your hand drill, but ones for drilling through rocks. And because rocks are very hard, you've got to have something very hard to go through them. And this is 2 drill bits. This is a brand new one. This one's diamond impregnated, and this is what happens after it's been grinding rocks for a little while, because rocks can be very hard. And each of these drill heads are worth a couple of $1,000 up to about $20,000 or $30,000 each, depending on their size. So you can make diamonds, and there's a little video on YouTube, but most diamonds are actually mined, but some people are making diamonds in the laboratory, and so you can watch that video to find out how they do that. And some of those human-made diamonds are used for industrial uses, and some of those industrial uses, for example, here's a scalpel that is impregnated with diamonds to make it quite hard, but it can also be very sharp as well. and this is a grinding wheel where these little chunks here are the diamonds and impregnated into a metal, and that diamond wheel can cut things like ceramics and glass and cement and just about anything. They do wear out, of course, because the metal wears away and the diamonds pop out, basically. Dentistry, if you've ever had a filling or dentist drill into your teeth, most of the drill bits will be impregnated with diamonds because the teeth are quite hard. And some people actually use diamonds for bling. Diamond files for filing very hard things, and these are grinding pastes. So when we saw those diamonds that were faceted, that you see in diamond rings and jewellery, how do you get those nice facets? By grinding them, but by using diamonds to grind onto diamonds, and these are different grades of grinding pastes. Now, the other commonly known covalent network substance is, of course, quartz, silica dioxide, and this is what it looks like. A very common mineral in rocks and in sand. Most beaches are made up of quartz crystals, and this is what it looks like. So you have your silica, and it wants 4 bonds, and so each of the 4 covalent bonds are with oxygens, and then one oxygen joins up, or the oxygen joins up with the silicon, so you get this arrangement, and there's probably a better diagram coming up here which is trying to show the 3-dimensional arrangement, very similar to the structure within diamond, but because you've got different atoms it's not as strong. Some of the bonds are a little bit weaker, and therefore it's not as hard as diamond. Still quite hard though. Okay. Some of the uses of quartz, well, on your watch you've got a thing that says quartz. That's not just a pretty label. Inside your clock is a little quartz crystal encapsulated here, a tiny little waver of quartz, and that oscillates when a current is put through it, through the electrodes. It oscillates at that many times a second, and that is what actually gives, there it is there, that's what makes your quartz watch very accurate, because what they do is they count those oscillations every second, and once they get 32,768 counts of vibrations, that's 1 second, and then they start counting again, and then another second, and so you can see it can be quite accurate, much more accurate than a mechanical clock mechanism. So what are the properties of covalent network lattices? We've just looked at 2 of them, diamond and quartz, and we recognize that they're very hard, and so they have a very high melting point. They occur as solids, have a very high melting point. Why do they have a very high melting point? Because of all those covalent bonds. And they do not conduct electricity because there's no free electrons. All those electrons are bound together in covalent bonds. But they are brittle. Diamond will shatter if you hit it incorrectly and with enough force, as will quartz. Chemically inert, so they generally don't react with anything. That's why rocks can weather and come down rivers and go through oceans and waves and things, and you still get quartz on the beach. All the other minerals have weathered away, but quartz is quite resilient in that respect because it's chemically inert and insoluble. Diamond and quartz are insoluble in water. So very high melting points is an important point, and the strongness of the covalent bonds makes them very hard. I should have put very hard here as well. So in the next video we're going to learn about covalent layer lattices. Cheerio!